Welcome to this JEE crash course. In today's session, let's discuss numerical problems based on work, energy and power. We had already discussed the related synopsis. We are familiar with the basic concepts and equations. Let us use these things to solve problems. Example 1. A person is holding a bucket by applying a force of 10 Newton. He moves a horizontal distance of 10 meter and then climbs up a vertical distance of 10 meter. Find the total work done by him. So the two journeys are like this. First he travels along this direction covering a distance of 10 meter. And then he covers this vertical distance of 10 meter. Find the total work done by him. Okay. Now, if you look at the work done by him, that is work done by his weight here. Suppose we consider this, he is traveling along this direction and his weight acts vertically down. So for the first part of the journey, if work done is W1, this is going to be Fs cos theta, that is mg into s into cos 90. As his displacement and the force are perpendicular to each other, the work done by him during this journey is 0. Whereas for the second part of the journey, let the work done be W2. So in this case it is mg into s into cos 180. That's right. This is going to be 180. So the work done by this person is opposite to the work done by the gravity, isn't it? So gravity tries to pull him down, whereas the person has to move in this direction. So work done by gravity is this much, while the work done by the person is mg into s into cos 0. How much is that? Mg. This is 10 Newton and this is 10 into 1, so it becomes 100 joule. So the work done by the person in lifting the bucket through a distance of 10 meter up is 100 joules. C is our correct choice. Example 2. A locomotive of mass m starts moving so that its velocity varies according to the law v is equal to alpha root s, where a is a constant and s is the distance covered. Find the total work done by all the forces acting on the locomotive during first t second after the beginning of the motion. So total work done by all the forces during first t seconds. Okay. Given that velocity is given by alpha root s. You know, the acceleration is nothing but dv divided by dt. That is nothing but alpha into half into s to the power of minus 1 by 2 into ds by dt. That is alpha into s to the power of minus 1 by 2 into v divided by 2. But v is also known to us, that is alpha root s. So alpha s to the power of minus 1 by 2, v itself is alpha s to the power of 1 by 2 whole divided by 2. And this simplifies to alpha square divided by 2. So acceleration is alpha square by 2. Therefore, what is the force? Force is equal to mass into acceleration, that is m alpha square by 2. And now, using the equations of motion, I can find out the distance it travels, which is ut plus half at square, half into a m, that is alpha square divided by 2 into t. And now this becomes, what is that equal to? T square, half alpha t square. So what is that equal to? Alpha square t square divided by 4. That's the distance traveled. And you know, work done is equal to force into displacement. Force has been found. What is that force equal to? Force is m alpha square by 2, m alpha square divided by 2, and the distance is alpha square t square divided by 4. Thus it becomes m alpha to the power of 4 into t square divided by 8. So m into alpha to the power of 4 into t square divided by 8. So which is our correct option? M alpha square t square, m alpha to the power of 4 t square divided by 8. A is our correct option. Example 3. A body moves from point A to B under the action of a force varying in magnitude as shown. Obtain the work done, where the force is in Newton and displacement is in meters. Okay. Now let us see how to do this one. You know, on force versus displacement graph, the work done is equal to area below the curve on Fs graph. So now we have to calculate the work done. It's simple. So I'm just showing the graph one more time for your reference. So we have to calculate this work done, and again this work done, and we have to subtract the same from this work done, because it's the negative work done. So clearly, what is that equal to? For the first part, it's a rectangle of sides 10 and 1. So 10 into 1 plus, this is a trapezium. So its area is half into 10 plus 15 into 1 plus, it's a triangle, half into 1 into 15, and finally the last part is a triangle minus half into 1 into 15, and this simplifies to 22.5 joules. So the work done by this force is 22.5 joules. C is our correct option. Example 4. An object of mass m kg falls from rest through a vertical distance of 20 meter and reaches with a velocity of 10 meter per second. How much work is done by push of air on the object? G is given. So let's calculate. So here the change in the kinetic energy is work done by the gravity plus work done by the push of the air. Correct? Work energy theorem. So according to work energy theorem, we can write work done by gravity plus work done by the push of the air is equal to change in the kinetic energy. But what is work done by gravity? It is mg into 20. That's right. So mg into 20. This is 20 mg. And the change in the kinetic energy. So it falls from rest. That means its initial velocity is 0. Final velocity is 10 meter per second. And therefore I can write it like this. How much is that? 20 mg plus work done by this one is W is equal to half m into 10 square minus 0 square, and upon simplification you get work done by the force as, how much is that? This is minus 730 joule. So minus 730 joule is the work done by the force, that is push of air. So A should be our correct choice. Example 5. A chain of length L and mass M lies on the surface of a smooth hemisphere of radius r which is greater than L with one end tied to the top of the hemisphere. Find the gravitational potential energy of the chain. Okay, we can show the construction. The hemisphere, shown a part of it, and there is a chain and it is fixed over here. This is R and this length is L. So the total length is L and its mass is M. Now we have to calculate the potential energy. So notice that different parts are at different heights. So what I am going to do, I am going to redraw the diagram first of all to show this one. So I am going to consider a small, this is the portion of course. So this is a small portion I am considering whose mass is dm, and let's assume that this portion is at an angle of theta and this subtends an angle d theta. So this is of length, I can write r d theta. R d theta is the length of this portion. And the corresponding mass is m divided by L into r into d theta. And this is at what height? Is it at a height r cos theta? This is r, so this is r cos theta. Therefore, the gravitational potential energy of this part is dm into g into h. That's nothing but m by L into r into d theta into g into r cos theta. That's the gravitational potential energy of this part. And the total potential energy is integral of this. A few terms come outside, m g r square divided by L into integral cos theta d theta from 0 to, and the corresponding angle, you may notice that this is L, this is R, this is theta. So L is equal to R theta. That is right. L is equal to R theta. So theta is equal to L divided by R. Let us substitute and simplify. mg r square divided by L integral cos theta d theta is sin theta from 0 to L by R, and upon simplification we get it as mg r square divided by L into sine of L divided by R. That is the total gravitational potential energy of the chain. Mg r square divided by L. So mg r square divided by L into, so you will notice that this is mg r square divided by L into integral cos theta d theta, and it further reduces to this one, mg r square divided by L into sine of L divided by R. Mg r square sine L by R. So B is our correct choice. This should be L, not 2. Example 6. A uniform chain of length L and mass M overhangs a smooth table with 2/3 part lying on the table. Find the kinetic energy of the chain as it completely slips off the table. Okay. The construction is here. 2/3 is present on the table. That means 1/3 is overhanging. Right? And the question is the kinetic energy of the chain as it completely slips off the table. Now we can say change in the gravitational potential energy is equal to change in the kinetic energy. Final kinetic energy is say K F. Initial kinetic energy is 0. So this is, I'll write it as change in the energy. So I'll write as UF minus UI. So I'll take this as 0 reference level, That's right. This is 0 reference level. So initial potential energy is 0. So I can say final kinetic energy is equal to potential energy. What is that equal to? So initial change in the potential energy. Initial potential energy is not 0. So UF minus UI is present. Now, what is UI equal to? UI is equal to, if you look at it, 1/3 is hanging. So M by 3 G L by 6, because the center of mass is at a distance of L by 6 and this is minus. Final potential energy is the entire mass comes down. So finally the entire mass comes down and this is G and this is at a distance of L by 2 down. Right? So kinetic energy finally is equal to UF, that is minus mg L by 2. That's going to be minus of minus mg L divided by 18. That's right. So the value of the final kinetic energy becomes, if you simplify it further, you get 4 by 9 mgl. The value of the kinetic energy becomes 4 by 9 mgl. So our answer is 4 by 9 mgl, which corresponds to option A. Example 7. A smooth rubber cord of length L whose coefficient of elasticity is K is suspended by one end from point O. The other end is fitted with a catch B. A small sleeve of mass M starts from point O. Neglecting the masses of the thread and the catch, find the maximum elongation of the cord. Okay. So let's show the construction here. This is a smooth rubber cord of length L whose coefficient of elasticity is suspended. So there is a cord or there is a wire. So I can show the wire like this. This is the wire. The other end is fitted with a catch B. So there is a catch here. So a support. And he says a small sleeve of mass M starts from the point O. Small sleeve starts from point O. This is point B, of course. Now, neglecting the mass of the thread and the catch, find the maximum elongation of the cord. Okay. Right? So this is the construction. So finally, this is the situation. This would have come here. This is B. Now, clearly, in this problem, there are changes in energies. Suppose I consider, say, Y as the elongation of the thread. Then from energy conservation, the decrease in potential energy of the sleeve is equal to elastic potential energy stored in the cord. That's right. So, decrease in potential energy is equal to elastic potential energy. That's the energy conservation. So, write mg into L plus Y. That's the change in the potential energy or decrease in the potential energy. That should be equal to half k y square. Half k y square. So if I simplify it further, I get half k y square minus mgy minus mgl is equal to 0, an equation, a quadratic equation in y. And the value of y therefore is equal to, what is it? mg plus or minus root of mg whole square plus 4 k by 2 into mgl divided by 2 into k by 2 minus b plus or minus square root of b square minus 4ac divided by 2a. Now, if you look at the quantity inside the square root, it is greater than 1 and therefore elongation is a positive quantity. So elongation is a positive quantity and therefore we can take that mg outside, etc., and simplify, and it becomes mg divided by k. This is 1 plus or minus square root of 1 plus 2kl divided by mg, right? So this becomes mg by k 1 plus root of 1 plus 2kl divided by mg, right? So this is our expression for the elongation of the string or elongation of the cord. It's our correct option A. Example 8. A 8 kg ball moving with a velocity of 4 meter per second collides with a 2 kg ball moving with a velocity of 8 meter per second in opposite direction. If the collision is perfectly elastic, what are the velocities of the balls after the collision? Okay. So this is a typical problem based on collision, and in collision we conserve momentum, and if it is an elastic collision we conserve kinetic energy as well. Thus I can write m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. So let us substitute that. 8 into 4 minus 2 into 8. Why? Opposite. m1 8 into v1 plus 2 into v2. That's right. And the collision is elastic. As the collision is elastic, this is your equation number 1. The collision is elastic, therefore kinetic energy is also conserved. Half m1 u1 square plus half m2 u2 square is equal to half, what's it going to be, m1 v1 square plus half m2 v2 square. That is half into 8 into 4 square plus half into 2 into 8 square is equal to half into 8 into v1 square plus half into 2 into v2 square. So I have two equations and two unknowns, and we can solve for this. We get minus 4 by 5 meter per second, and v2 is equal to 56 divided by 5 meter per second. This is method 1. So in this method, what do? We write the equation separately, right? We write the equation separately, and then we write the actually what we have done is we have written the equation for momentum conservation, we have written the equation for what else, energy conservation. So if I consider the direct equation, method 2, we can write the equation directly. What is that? v1 is equal to m1 minus m2 into u1 divided by m1 plus m2 plus 2m2 u2 divided by m1 plus m2, and v2 is equal to, what is it going to be, 2m1 u1 divided by m1 plus m2 plus m2 minus m1 into u2 divided by m1 plus m2. So if you remember this set of equations, it becomes pretty easy. So you can substitute for these two equations directly, and you can get the answer in one step. But remember this equation, you have to probably write these equations a couple of times before you memorize them. So the speed of the second particle after the collision is 56 divided by 5, whereas that of the first is minus 4 by 5. He is given option corresponding to that of the second one, and thus 56 divided by 5 meter per second is our answer. Example 10. A smooth washer impinges at a velocity v on a group of 3 smooth identical blocks resting on a smooth horizontal surface as shown. The mass of each block is equal to the mass of the washer. The diameter of the washer and its height are equal to the edge of the block. Determine the velocity of the blocks after the impact. Okay, so remember, this actually strikes 3 and 2. Actually, it comes in contact with 3 and 2. So this is how the construction can be done, right? It doesn't come in contact with 1. Okay, now, so what happens is that the washer collides with the blocks 2 and 3 symmetrical, and therefore both will move with the same speed. And okay, let us draw the diagram and show the construction. So the situation can be shown. Yes, this is one block, this is the other one, and we have the third block like this, and it comes along this direction and collides. So I have this colliding here, and when it collides, of course this entered with velocity v, and this moves with velocity v dash, and this moves with velocity v dash c. Correct? And clearly with respect to this line, this angle is 45 degree, isn't it? This angle is 45, and this is also 45. So now let us assume that, or let us conserve the momentum along this line. Say I'll call this as x-axis. So momentum along x direction is conserved. What is the initial momentum? Initial momentum is mv. That must be equal to mv dash cos 45 plus mv dash cos 45. So we have mv is equal to 2m v dash cos 45, that is 1 by root 2, or we have v dash is equal to v divided by root 2. V dash is equal to v divided by root 2 is our expression for the final velocity of this block, which actually is our option D. Next one. Two identical cylindrical vessels with their bases at the same level each contains a liquid of density rho. The height of the liquid in one vessel is h1 and that in the other vessel is h2. The area of either base is A. The work done by gravity in equalizing the levels when the two vessels are connected is. Okay. So we can show the construction. So liquids are occupied up to height h1 and h2 respectively. Assume that there is a stopcock, and after the stopcock is opened, the final level becomes, say, h. So the final level is h at a height h. This corresponds to the final level. Now clearly the work done by gravity in equalizing the levels is equal to change in potential energy, final potential energy minus initial potential energy. Now potential energy can be written as mgh. Here mass can be written as area into height into density into G into H. But you should be careful about this side and this side, those two are not same, we'll take up that. So initial potential energy is equal to this is rho into A into H1, that gives me mass, into G, H1 divided by 2 because its center of gravity is at a distance of H1 divided by 2 from the bottom, plus rho A H2 into G H2 divided by 2. This is the initial potential energy. Likewise, the final potential energy is, there are two columns, each contain liquid to a height h, therefore 2 times rho A H, that's right, rho A H into G into H by 2, because now it is at a height of H by 2. Where, how to find that H, which is H1 plus H2 divided by 2 clearly. Simply volume conservation. So H should be equal to H1 plus H2 divided by 2. So if I substitute those details, UF minus UI, that is nothing but rho G A by 2 into rho G A divided by 2 into H square divided by, 2 times H square, minus, this is the final potential energy, minus initial potential energy is rho G A divided by 2 into H1 square plus H2 square, where that H1 again is H1 plus H2 divided by 2. So if you substitute and simplify, you get as 1 by 4 H1 minus H2 whole square into rho into A into G. So you can check it for yourself whether the work done turns out to be this or not. So the work done is 1 by 4 H1 minus H2 whole square into rho into A into G. So D is our correct option. Next one. An object is attached to a vertical spring and slowly lowered to its equilibrium position. This stretches the spring by x. If the same object is attached to the same vertical spring but permitted to fall suddenly, the spring stretches by. Okay. So in the first case, what are you doing? You are slowly releasing this spring such that it comes to the equilibrium position and the elongation is x. While in the second case, you have released it and it comes to this position. So the question is, what is this x dash? Now here, as it comes to the final position, it is in equilibrium. So I write mg is equal to kx, right? Therefore, x is equal to mg divided by k. That's my equation number 1. Whereas in the second case, there is a fall in gravitational potential energy or change in gravitational potential energy, which is mg x dash. And that gets converted into spring potential energy, half k x dash square. So what I have? X dash is equal to 2 mg divided by k, equation 2. Therefore, x dash divided by x is equal to 2 mg divided by k, that is x. So this is nothing but what is this? So this 2 mg and this 2 mg cancel here. So what do I have? X dash is equal to 2x. So this does not appear here. So x dash is equal to 2x. So the distance traveled is 2x, or the elongation of the spring is 2x. C is our correct option. Next. A body of mass m as shown in the figure with a small disk of mass m placed on it rests on a smooth horizontal plane. The disk is set in motion in the horizontal direction with velocity v. To what height relative to initial level will the disk rise after breaking off the body m? This is m. The friction is assumed to be absent. Okay. Basically, we can find out using conservation of momentum the velocity with which it starts rising, and using energy conservation we can find out the distance it rises. So it's basically conservation of momentum and conservation of energy. So let us look at it. Now let us apply the conservation of momentum, according to which initial momentum is equal to final momentum of the system. So this is the initial momentum of the disk. Final momentum of the system is m plus m into v dash. So I have v dash is equal to mv divided by m plus m. So that's the speed with which it starts moving. So now let us apply conservation of energy. Suppose the disk rises to a height h, let's assume, then initial kinetic energy should be equal to final kinetic energy plus final potential energy. What is the final kinetic energy? Half m plus m into v dash square plus rise in gravitational potential energy is mgh. So we can substitute here half mv square is equal to half m plus m into v dash is mv divided by m plus m square plus mg into h. I can simplify this one, and upon simplification you get h as mv square divided by 2 times m plus m into g. So the height to which it rises is nothing but mv square divided by 2 into m plus m into g. So C is our correct choice. Next one. A force F is equal to minus K of yi plus xj, where K is a positive constant, acts on a particle moving in the xy plane. Starting from the origin, the particle is taken along the positive x-axis to a point a comma 0, and then parallel to the positive y-axis to a point a comma a. Calculate the total work done by the force on the particle. So what is the force acting? This is the force acting. Look at it. Is it a constant force or is it a variable force? Obviously it is a variable force, right? Let us see how to represent this to find out the total work done. So now we can simplify it like this. Clearly, displacement vector can be written as dxi cap plus dyj cap, because eventually we are going to use the idea f dot dr integral to find out the work done. That's right. So the displacement vector is given by this equation. So work done is equal to integral, there is a negative sign, minus k into y dx, right, plus x dy y into, okay, I will write it here, work done is equal to minus k into yi plus xj dot dxi plus dyj. I am writing everything in detail. That turns out to be minus k comes outside, and I am left with integral y dx plus x dy, and the limits are from 0 to 0, 0 to a comma a. Now look at it, minus k integral 0 0 a. Now look at this term. This is a beautiful term. Now can we write this term as differential of xy? Is that possible? Because you know differential of xy is x dy plus y dx. Product rule. So this is d of xy. Now you have integral and a differential together. If you are integrating a differential, the function is the answer. So it simply becomes minus k, integral and differential vanish, leaving xy from 0 0 to a comma a. So these two are gone. I'm left with minus k. This is xy, x is a, y is a, and what is it going to be? So a comma a, that is a into a, minus 0, that is minus k a square. So the work done is equal to minus k a square. So we have minus k a square as the answer. 15. A particle of mass 0.5 kg travels in a straight line with velocity v is equal to a x to the power of 3 by 2, where a is 5 m to the power of minus 1 by 2 s to the power minus 1. So he has given the value of a, of course. He has some value. What is the work done by the net force during the displacement from 0 to x is equal to 2? Okay. Now work done again is integral f dx. So to get this I need the acceleration, and I find the acceleration because the velocity is given. Let us see how to do this. Velocity is equal to a x to the power of 3 by 2, and you know you can write acceleration as dv divided by dt, or I can write v dv divided by dx, anything is fine. V dv divided by dx. So if I take this v is a x to the power of 3 by 2 itself. I am going to differentiate it with respect to x. So 3 by 2a into x to the power of 3 by 2 minus 1. That's right. So I have a 3 by 2 has already come there, a square, and then x to the power of 3 by 2 minus 1 is x to the power of 1 by 2, and then what do I have? X to the power of 1 by 2 plus 3 by 2, x to the power of 4 by 2, or simply x square. So 3 by 2 a square x square, that is the acceleration. And therefore force is mass into acceleration, that is 3 by 2 m a square x square. So I have the force, I know the acceleration, and therefore I can find out the work done simply by integrating f dx from 0 to the final value is 2. What is it? Force is 3 by 2 m a square x square dx. 3 by 2 m a square, come outside, integral x square dx is x cube by 3. So x cube divided by 3 from 0 to 2, and this becomes m a square divided by 2. M a square divided by 2 into, this is 8. So you can substitute for all these details. Do we know the mass? Yes, we know the mass, 0.5. Do we know the value of a? Yes, a square is 25 divided by 2 into 8, right? So you can simplify it further and you will end up with how much? 50 joules. Yes, this turns out to be 50 joules. B is our correct option. Next one. Under the action of a force, a 2 kg body moves such that its position x as a function of time t is given by x is equal to t cube by 3. So position is given by x is equal to t t cube divided by 3. X is in meter, t is in second. Calculate the work done by the force in the first 2 seconds. Okay. Similar approach. Work done is equal to integral f dx is what I am going to use. Force is mass into acceleration. So I need the acceleration. And because I am given x as t cube by 3, I will get the velocity, which is dx by dt. Dx by dt is, how much is that? Differential t cube is 3t square. So I have t square. That's right. And what is the acceleration? This is 2t. And thus I have force is equal to m into a, and this is m into 2t or 2m into t. That's the force. And now work done is equal to integral f dx. Integral f 2m into t dx. Now we know that x is given to us. So this v is nothing but dx divided by dt. Therefore, what is dx? Dx is nothing but t square dt. So I'll write as t square dt. And what are the limits? 0 to 2. So what are all the terms which go outside? 2m goes outside. And we are left with integral t cube dt from 0 to 2. So 2m integral t cube is t to the power of 4 divided by 4 and 0 to 2, and we can substitute for all those details, and upon substitution I am writing it directly. I want you to substitute and get the answer and check it for yourself, and it turns out to be 16 joules. So we have done a couple of problems which are repetitive in kind. Try to remember the approach. In all these problems, probably distance is a function of time, or velocity is a function of time, or velocity is a function of x, etc. But remember, the approach is like this: get the acceleration, get the force, and then write it as integral f dx. So the answer for this problem is 16 joule. D is the correct option. Next one. A rod of mass m and length L is held vertical. Find its gravitational potential energy with respect to zero potential energy at its lower end. Okay. So the rod is like this. It is held vertical, and the length of the rod is L, its mass is m, and this is treated as 0. Now, you know, potential energy is given by mgh, the mass is mg, and while measuring the potential energy, remember, center of mass is the reference position, which is at a height L by 2. So L by 2 mg into L by 2. So mg into L by 2 should be our answer. Actually, you can arrive at this by the proper method like this. To do this, what you are going to do is take an element of mass dm located at a height, say some y, and clearly the mass of this element dm can be written as m divided by L into dy. So gravitational potential energy of this element becomes dm into g into y, that is m by L into dy into g into y, or this becomes mg divided by L integral y dy, and this becomes 0 to L, and upon simplification you get as mg into integral y dy is L square by 2, so I am left with L, and mgl divided by 2 should be the answer. Simple problem, but remember the approach. mgl divided by 2 is our answer. Example 18. A machine gun fires 60 bullets per minute with a velocity of 700 meter per second. If each bullet has a mass of 50 gram, find the power developed by the gun. Okay. So, momentum conservation. Here it's basically power calculation. Power is equal to work done divided by time. Work done is nothing but change in kinetic energy, which is half mv square divided by time. What is that equal to? Half, and this m, what is that m here? So now how many bullets are sprayed? 60, and mass of each is 50 gram. So if you simplify this, it becomes 60 into 50 divided by 100 into v square. What is that? That's nothing but 700 square whole divided by, he says, per minute, so 60 seconds, and therefore it becomes half into 60 into 50 by 100 into 700 square divided by 60. So you can simplify it further, these two cancel, and we are left with 1 by 4, 700 square divided by 1 by 4, and it becomes 12,250 watt. So I want you to check it for yourself. This is our this is the power delivered by the gun. A railroad car traveling at 32 km per second runs into a stop at a railroad terminal. A vehicle having a mass of 1800 kg is held by a linear restoring system that has an equivalent spring constant of 20,000 Newton per meter. If the railroad car is assumed to stop suddenly and the wheels on the vehicle are free to turn, what is the maximum force developed by the equivalent stopping system? Neglect the friction and the inertia of the wheels. Okay. So what he is indirectly saying is that force has to be calculated, right? The maximum force has to be calculated. So to calculate the force, spring constant being known, I need to find out the maximum compression that is possible. To find out the maximum compression possible, let us use conservation of energy, according to which kinetic energy gets converted into spring potential energy, right? So this gives me x is equal to, what is it going to be? X square is equal to mv square divided by k, or v root m divided by k. So we have found the value of this one, and therefore the maximum force that is possible is k into x. K into, what is the value of x? We found it as root m into k. So simplification, velocity, what is that? 32 km per hour. So of course k is there, I will take that inside. You can write v root of m k to the power of 3, or you can substitute there only, anything is fine. So this turns out to be 32 km per hour. 32 into 5 by 18, square root of mass, what is that? Mass is equal to 1800 kg into, what is the spring constant? Spring constant is nothing but 20,000 to the power 3, and you can simplify it further. It turns out to be 53.3 into 10 to the power of 3 Newton. If you simplify it further, you get 53.33 to be specific, 53.33. So 53.33 into 10 to the power of 3. Next one, a chain of mass m is equal to 0.8 kg and length 1.5 meter rests on a rough surface table so that one of its ends hangs over the edge. The chain starts sliding off the table all by itself provided the overhanging part equals mu is equal to 1/3 of the chain length. What will be the work performed by the friction forces acting on the chain by the moment it slides completely off the table? Okay. So the construction can be shown like this. He says that initially 1/3 hangs over, so that one of its ends hangs over the edge, and overhanging part equals 1/3 of the chain. The chain starts sliding off the table provided the overhanging part is L by 3. L by 3. So if L is taken as this length. What will be the total work performed by the frictional forces acting on the chain by the moment it slides completely off the table? Okay. Now, if we consider, so first of all, we need to find out the total work done. Here he says work performed by the friction, which means that we need to find the coefficient of friction. So the force of gravity acting on the hanging part, on this part, causes the tension in the chain in the remaining part, and that is equal to the frictional force on the chain lying on the table. That means the mg on the hanging part is equal to tension, which is equal to force of friction on the part which is present on the table. So let's write this. This is mg by 3 because 1/3 is hanging. That must be equal to mu into n. So mg by 3 is equal to mu into n. What is the normal reaction on this part? That's nothing but, how much is that? Is it 2 mg by 3? Yes, because 2 m by 3 is present on this one. So what do you get? I get mu is equal to 1 by 2. That's the coefficient of friction. Coefficient of friction is this much. Now, suppose we consider a small part. Then let's assume that this is the part under consideration and its length is some dx, and this part experiences force of friction, and that force of friction can be calculated, and we can also calculate the work done. Let's see how to calculate that one. So work done is equal to F into dx, and clearly force of friction and displacement are opposite in direction because force of friction tends to pull it back while the displacement happens along this direction. That's right. So with a negative sign, that is cos 180 watt, minus this is mu n into dx minus mu into n. Normal reaction is equal to clearly mass of this part into g. That's right. What is that mass? So I can write as lambda dx into g, where lambda is total mass by total length into dx into g. So I'm just writing it as lambda. So this becomes lambda into dx into g. Lambda into dx into g. Right? So we have this equation lambda into x into g. I'm sorry, lambda into x into g, because I'm considering a part which is of length x, which undergoes a displacement of dx. Right? So if you simplify it further, we have mu lambda x into g into dx is present here. That is the work done on an elementary part. So total work done is equal to minus mu lambda g into integral x dx, and how much part is to travel. The length of the part which travels is starting from x is equal to 0, and the final part is 2x divided by 3, that is 2l divided by 3. So 2l divided by 3, that is minus mu lambda g, and integral x dx is x square by 2, 0 to 2l divided by 3. So you can simplify it further. Upon simplification, I want you to try this. Remaining part, of course, this becomes minus mgl divided by 9. So you can substitute for these details here, and this is minus mgl divided by 9. Are we given the value of m? The value of m, that is the mass of the chain. Mass of the chain is 0.8. We know this. Length of the chain is 1.5 meters. So we can substitute and simplify this, and we get it as minus 1.306 joules. That is our answer. Minus 1.306 joules is the answer for this part. Next one. A 70 kg man leaps vertically into air from a crouching position. To take the leap, the man pushes the ground with a constant force F to raise himself. The center of gravity rises by 0.5 meter before he leaps. After the leap, the center of gravity rises by another 1 meter. The maximum power delivered by the muscles is. Let us see. Now, if you consider the power dissipated, how to find out the power dissipated? The power dissipated is, work done divided by time. Work done is nothing but increase in its potential energy, so I will write it as mgh. What is that? M 70. G I will take 10. H 1.5. How is it 1.5? The center of gravity rises by 0.5 meter before he leaps, and after he leaps, the center of gravity rises by another 1 meter. That's right. So this is equal to the work done, which can be simplified 1.5 into 7, that is 105 into 10 into 10. So we have 1050 joules. And we also need time. How to do that? Simple. This can be calculated using your simple equation of motion. S is equal to ut plus half gt square. That gives us t is equal to root of 2 s divided by g. Now the value of s is nothing but 1 meter. So divided by 10, and that gives you t is equal to root of 0.1, which further reduces to 0.316 seconds. So upon simplification, we get power dissipated as work done divided by time. Work done is 1050 divided by the time taken is 0.316, and it reduces to 3.3 into 10 to the power of 3. So during the takeoff, the power dissipated is 3.3 into 10 to the power of 3 joule per second, that is watt. So 3.3 into 10 to the power of 3 watts at the takeoff. So during takeoff, this is 3.3 into 10 to the power of 3. 22. A wind powered generator converts wind energy into electrical energy. Assume that the generator converts a fixed fraction of the wind energy intercepted by its blades into electrical energy. For wind speed v, the electrical power output will be most likely proportional to. Okay. Remember, we had come across with a problem of this kind. You know, the power is nothing but work done divided by time. Work done is nothing but change in kinetic energy. Change in kinetic energy is nothing but final kinetic energy minus initial. Remember, we had come across this kinetic energy, which is given by half rho A V cube. Remember, half rho A V cube, and this is divided by T. So if you simplify it further, we get power is directly proportional to V cube. A very simple problem. Power is directly proportional to V cube. C is our correct choice. Next, a block of mass 0.1 kg is connected to a spring of unknown spring constant. It is compressed to a distance x from its equilibrium position and released from rest after approaching half the distance, that is x by 2, from equilibrium position. It hits another block and comes to rest momentarily while the other block moves with a velocity of 3 meters per second. The total initial energy of the spring is, it says, a block is connected to a spring, is compressed to a distance x from the equilibrium position and released. After approaching half the distance from equilibrium position, it hits another block and comes to rest momentarily while the other block moves with a velocity of 3 meters per second. Right. So clearly, in such problems, the idea of conservation of momentum and conservation of energy are useful. So if you look at the conservation of momentum, we have m1u1 plus m2u2 is equal to m1v1 plus m2v2. So what are these things? What is the value of m? m1 0.1. What is its initial velocity? Don't know, we have to find out. m2 is m into 0. This is equal to, he says, it comes to rest momentarily, so I'll write 0.1 into 0 plus m into 3. So we have the relation between them. 0.1 u is equal to 3m. 0.1 u is equal to 3m. Now, we can also make use of the energy conservation. Half mu square should be equal to half mv square. Right? Half mu square is equal to half mv square. So how do we find it out? Now we know that half 0.1 u square is equal to half m. This is 3 square. So upon simplification, we get u is equal to, we know the value of u and m are related by this equation. So I can say m is equal to 0.1 divided by u. This gives me m is equal to 0.1 u divided by 3. That is right. So you can go here and it gives us u is equal to 3. Now the total initial energy of the spring. So total energy of the spring initially is equal to half k square, which is nothing but half mv square. So because the total energy is conserved, I can say half mv square, half mu square gives us the energy. And we know this value, half, this is 0.1, and we have calculated the value of u, and the value of u turned out to be 3. So how much is that? So it becomes 0.6 joules. 0.6 joules. Next one. A block of mass m is equal to 2 kg is connected to a spring of force constant 50 Newton per meter. Initially the block is at rest and the spring has natural length. a constant force of 60 Newton is applied horizontally towards right, the maximum speed of the block is. Okay. So you are applying a constant force of 60 Newton along this direction and the spring is in its natural length. Initially the block is at rest, of course. Now, when this force is applied, when a constant force is applied, there is an elongation. What is that elongation equal to? This is given by F divided by K. What is that? 60 divided by 50, that is 1.2 meter, or 6 divided by 5, 1.2 meters, 6 divided by 5. Now, we can use the conservation of energy. What does that give us? The total initial spring energy is equal to final energy kinetic, which is kinetic energy. That is right. So, we have to find out the maximum speed of the block. We need the value of this one. So, what is that? Half k x naught square. Do we know this one? So, we can simplify this one directly. We can write V naught therefore is equal to, half and half cancel here, these two cancel, and V naught is equal to x naught root of k by m. So, x naught root of k divided by m, and we have found the value of x naught, which is 6 by 5. K is known to us. What is the value of k? K is 50. The mass of the block is 2. So, if I simplify it further, 25, 5 and 5 cancel, and this gives us 6 meter per second. So, the velocity, the maximum speed of the block turns out to be 6 meter per second. So, this should be meter per second. So, the maximum speed of the block is 6 meter per second. Water through a well is lifted through 10 meter and delivered with a velocity of 10 meter per second. If 10 liter of water per second is supplied, the power in kilowatt of the motor is. Okay. We can again make use of energy conservation here. Water is lifted and it is delivered with a velocity. So, work is done to provide kinetic energy and to lift it. Work is done to provide kinetic energy and to lift it. What is that kinetic energy? It is half mv square, and this is mg into h. And power delivered is work done divided by time. So, I am going to write 1 by t, half mv square plus mgh. We can simplify it further. This becomes m, I can take t outside, we are left with v square by 2 plus gh. Mass is known to us, 10, and this is 1 second per second, of course, into v square divided by 2, 10 square divided by 2 plus 10 into h. The what is this one? Lifted through 10 meter. So, if I simplify this, 50, 150 and 150 into 10, 1500 watt. So, 1500 watt is the power. So, the power required is 1.5, that is 1500 watt, which actually corresponds to 1.5 kilowatt. So, 1.5 kilowatt is the answer for this one. B is our correct choice. Well, with this problem, we have come to the end of this session. But please go through all these problems one more time. Remember the basic ideas. Most of the times we use energy conservation, work energy theorem in solving the problems here. Sometimes you may also notice the usage of momentum conservation to arrive at the required answer. So the key ideas are very simple. Usage of work energy theorem, usage of conservation of mechanical energy, and the usage of momentum conservation. All the best. Thank you very much.